Hello, my name is Dominik Schön from the Technical University of Darmstadt Tele Cooperation Lab, and today I will present to you my work Tailor Twist, Assessing Rotational Media Interactions for Augmented Reality. The work was created together with Thomas Kosch, Florian Müller, Martin Schmitz, Sebastian Günther, Lukas Bommhardt and Max Mühlhäuser. Mid-air gestures are arguably the central interaction techniques of today's augmented reality head-mounted displays, allowing users to directly manipulate virtual interface elements within their arm's reach. However, while this type of input enables fast and easily adaptable interactions, it imposes strain and fatigue on the user's shoulders and arms, ultimately leading to discomfort when used for prolonged time. Prior work contributed metrics to assess these kind of strains for arm movements of such mid-air interactions. However, these works only look at the arm movements and postures, yet our interaction with augmented reality interfaces is typically more complex. Today's mid-air augmented reality interaction often involve translation, pinching, grab, zooming, and rotation gestures to control the virtual world. In particular, such rotational manipulations are among the most demanding since they require very complex hand and finger movements and require users to move their complete arm, partially their thorax as well. Even though today's mid-air gestures make heavy use of such rotational interactions, we still miss an in-depth understanding of their impact on the ergonomics. Therefore, in this paper, we systematically investigate the effects of mid-air rotation interaction in AR on discomfort accuracy and user behavior. As a result, we provide three contributions. First, a systematic evaluation of perceived ergonomics of mid-air rotations in AR varying pose, task alignment, and position. Second, a proposed design space for ergonomic-aware rotational mid-air interaction based on the study results. And lastly, a set of recommendations for future ergonomic-aware AR interfaces. For our user study, we created an AR rotational task inspired by the layout of a function and the functionality of real-world rotational knobs. Each knobs were represented by a white cylindric body, a gray cylindric axis around which the knob could be rotated, and finally a blue box as a current value indicator and an orange box with a 60 degrees offset for the desired final rotation. Participants were asked to grab the knob at the white body and rotate the knob until the blue and the orange box would align. Participants were free to re-grip as often as they want until they were satisfied. To place the tasks around our participants, we defined two reach distances. The far reach distance was determined by the full arm length of our participant. This reach distance is described by a half sphere in front of the participant with the radius of an arm length and the middle point between the shoulder blades. The near reach distance was determined by the lower arm length and describes a second, smaller half sphere. As exploring the whole arm-reachable space for interaction results in an infeasible number of possible locations, we discretized the two half-spherical shaped reach distances as follows. We placed 27 points equidistributed on the half-sphere. All these points are part of either the inner radius, the middle radius, or the outer radius. In total, we sampled the arm-reachable space at 54 points, which is the maximum number to keep the user study in a reasonable time frame. As the task's axis of rotation might alter the interaction performance, we further vary three axes of rotation of the task's controls: X, Y, and Z. The Z-axis is defined as the normal vector on the half-spherical surface of the reach distance. The x-axis is defined following the parallel of the spherical surface, while the y-axis follows the meridian. Lastly, we vary two stances, seating and standing. Standing allowed our participants to move freely and rotate their whole bodies when performing an interaction. In contrast, when sitting, participants were placed on a bar chair with no backrest and locked in orientation. This prevented the participants from rotating their lower bodies and hips, forcing the participants to perform rotations only with the upper body. These stances map to either on-the-go usage, like walking around, and stationary usage, like sitting in a bus or at a table in a confined space. Combining all independent variables, we have a total of 324 conditions, which also represents the trials for each participant. For each of these conditions, we logged the following dependent variables. We asked the participants about the perceived comfort on a Borg 10 scale after each trial. Further, we measured the final offset of the knob to the target rotation, described as the accuracy. And finally, we also logged the number of interactions, or how often the participants regripped during the trial, and whether they used the dominant hand or not. We analyzed the collected data using four-way repeated measures ANOVA, Poisson regression model, and a generalized mixed effects model. The analysis revealed several interesting things, of which I would like to highlight the most important ones. First, keep the interaction close to the body, especially when seated. We found out that interaction on the near reach distance increased the comfort by up to 22%. We observed a less severe effect when standing of only 5%. This indicates that participants used the freedom to move around and make themselves the interaction more comfortable in the standing stance. However, doing so implies minor negative effects on the comfort. Second, interactions further away from the body can still be precise. When standing, the accuracy of the close and far reach distance are comparable. This again shows that the participants used their freedom to move around in order to complete the task better. However, it also comes with the already mentioned penalty in comfort. Third, rotate around the upper axis to reduce the number of interactions needed. When rotating around the upper axis, participants required up to 14% less number of interactions until the task was finished. However, we found no comfort relation between the different axes. We assume that the physiology of the human body allows users to rotate around the upper axis more easily and further compared to other axes, thus resulting in better or faster interactions. Lastly, utilize the non-dominant hand. Users like to use the dominant hand whenever possible. However, when seated, participants start to use their non-dominant hand when the task is too far away from the dominant hand. As soon as the task crosses the non-dominant hand shoulder, participants use the non-dominant hand 50% of the times. Outside of the elbow of the non-dominant hand, the probability increased to 75%. These are four of the main findings of our work. For more information and further details, we refer to our paper. With that, I would like to thank you for your attention, and if you have any questions or comments, feel free to contact me.